Hi everyone, I'm Jan Ertol. I'll present our work FastSpec, Scalable Generation and Detection of Spectre Gadgets. This is a joint work with Berk Gulmezoglu, Koray Yurtseven, and Berk Sunar. Most of the modern CPUs has an optimization called Speculative Execution to increase the performance. Suppose this is the function written in C in your computer, and this function gets a user input X. Array1 size is a variable in the memory, and we assume it's not in the CPU cache yet. We have a condition that depends on X and array1 size variables. But since array1 size variable is not in the cache, CPU cannot evaluate this comparison. If we had an in-order processor, we would have to wait until it fetches this variable from the memory. But modern CPUs are much faster than the memory, and we can't afford waiting anymore. So instead of waiting, our CPUs just predict the outcome of branch condition and continue execution. In 2018, Koray et al. Showed that it is possible to exploit speculative execution. Assume there is a secret data beyond the array1 size in the memory. An adversary can simply cause misspeculation and make the processor execute this line, even with an out-of-bounds input. Then, using the cache timing side channel, while accessing array 2, the adversary can obtain the secret data. To mitigate this attack, several software-based techniques are proposed. Now, if someone shows us a potentially vulnerable piece of code, we know how to patch it. But we also know the same vulnerability can appear in different forms in the wild. The problem is we only have a limited number of examples that can guide our research. Therefore, we need to expand the number of vulnerable examples. We took those 15 examples in C and compiled them with different compilers. And for each compiler, we have used different levels of optimization. After that, we insert random instructions and operands into random locations of each assembly code and test them if they are still executable without an error. And most importantly, we test them if they still leak the secret information through speculative execution. At the end of this process, we obtained over 1 million different code snippets that are exploitable using Spectre variant 1. To use in the future experiments, we disassembled the Linux binaries to obtain a benign dataset. In total, we collected over 100 million lines of assembly code, and the datasets are available on GitHub. To further increase the variations in the generated gadgets, we trained a generative adversarial network. GANs are shown to be successful at generating unseen image and text by previous research. Typically, they have two separate models and they are trained together in a zero-sum game. While the generator learns to generate real-looking examples, the discriminator model learns to differentiate if a given sample is real or artificially generated. In our work, we have adopted a type of conditional GAN proposed by Fedus et al. In ICLR 2018. To input the assembly functions that we have created, we tokenize each instruction. For example, if there's an instruction like this one here, the opcode, parentheses, the commas, and the register names are counted as separate tokens. To limit the number of possible tokens, we represent the immediate values and labels with special tokens. Also, we represent the instructions or operands that are not frequently used with unknown label. Our Gadget generator framework has a generator and discriminator model. And let's say we have a piece of assembly code here. A random contiguous part of it is replaced with the mask tokens and given to the encoder part of the model. It is expected to fill the missing parts in the decoding stage. The internal structure of discriminator is very similar, except this time we input the generated examples and discriminator predicts if it's a real sample or not. The details of the SpectreGAN are explained in the paper. After 3 days of training our network, we achieved to be able to create assembly functions with the correct syntax without any supervision. In the generated samples, 70% of the compiled samples were correctly having the properties of a Spectre gadget. To evaluate SpectreGAN, we have used three different analysis approaches. First, we looked at the number of unique engrams. By engram, we mean a unique permutation of n tokens. When n is 5, in the base examples, we had 4.7 thousand unique engrams. Mutational fuzzing and SpectreGAN produced around 2 million new unique engrams. In the microarchitectural analysis, we examined the generated samples using hardware performance counters. We have used the number of issued microoperations and the number of retired microoperations. The microoperations executed in the speculative domain are excluded in the retired ones. Therefore, we can see that both fuzzing and SpectreGAN generated relevant gadgets while increasing the variety. Finally, we evaluated OO7 and Spectre tools with a subset of our dataset. And we showed that the conditions that can bypass these tools. You can see the detailed results in the paper. After creating a Spectre gadget dataset, the main problem still lingers. How do you find the gadgets in the wild? We can put elfans after every branch to block speculative execution, but it causes too much performance overhead. Or we can build a tool to find them, and we want to make it automated, scalable, and as accurate as possible. To contribute the solution of this problem, we propose the first and only deep learning-based detection approach to scan binaries for Spectre vulnerability, and we do it with linear complexity. We use the same tokenization method as before. After training with both benign and Spectre gadget examples, each instruction and operands are represented with a vector. Here we visualize those vectors by reducing dimensions using TSNE algorithm. As you can see, the vectors that belong to similar instructions and registers are closer to each other. This shows that our model is trained successfully to learn the semantics of assembly language. To scan a binary file, we first disassemble them, and after tokenizing, we input them to FastSpec as sliding windows. To demonstrate what we expect from our model, we insert a known Spectre gadget into a binary file. As you can see, our model gives high confidence rate in the windows that includes a Spectre gadget. In the first case study, we used OpenSSL speed benchmark. To evaluate the classification performance, we choose the findings of SpecFuzz as the ground truth. When we select the window size as 80 tokens, we achieve 0.04% false positive and 2% false negative. We also compared FastSpec with other tools in Phoronix test suite. We showed that taint analysis and symbolic execution-based tools show exponential behavior in the analysis time when the number of branches increase. For example, in the Crafty benchmark, the binary file size is only 0.6 megabytes, and it includes 10,000 branches. When we run Spectator on Crafty benchmark, it finished after 2 days. For OO7, we terminated the analysis after 10 days. On the other hand, it takes only under 6 minutes to scan for FastSpec. In terms of scalability, FastSpec achieves the best results in all benchmarks. Although the best precision and recall rates of the tools differs in different benchmarks, FastSpec achieves the highest precision and recall rates on average. In conclusion, we generated a Spectre gadget dataset. We introduced generative adversarial network for task-specific assembly code generation. And finally, we proposed a deep learning-based detection tool against Spectre variant 1 attack. You can find our dataset and all the code in our GitHub repository. If you have any questions, please do not hesitate to contact me. Thank you for listening.